Okay, so today we're looking at polar equations and graphs. The first thing that we're going to be looking at is what is a polar graph, okay? Then we'll look at how do we convert between polar graphs and the usual XY coordinates. We'll look at distances with polar coordinates, and we'll look at polar rows, limacon, and also a couple other different types of polar curves, okay? The polar coordinate system is still representing the same point. So if I pick on this T coordinate, right, if I pick a certain point, we've always learned to represent that with an X horizontal coordinate and a Y vertical coordinate, right? Another way that you could represent that point would be to find the angle from the horizontal that would have a line that sends it straight out through that point, and then also give it what radius it's at. So how far out on that line is it as in terms of a radius around the origin, okay? So your new points are going to be given a radius and an angle, and you should still be able to locate that point then that way. Some people ask, why do we even bother with this polar coordinate? I'm doing just fine with the XY. The graphs that I mentioned at the end are graphs that it would be really difficult, and I'm not even sure if it's possible, to graph on a rectangular grid. So remember, your rectangular coordinates are your XY. That's what we usually work with. The polar coordinates make it much easier and possible in a lot of cases. So there are some graphs where you can graph it polar or you could graph it rectangular, and there are going to be some where it would be really tricky, if not even possible, to graph it on a rectangular. Some key points, and please don't take the time to write all of this down. Paraphrase it, you guys. Listen to what I'm going to tell you and paraphrase it. Okay, what this whole thing up here says is that if you have a positive radius, then that just means that, like, let's say I give you this angle theta, which looks to me to be 45 degrees. So pretend that theta was 45 degrees. If I give you that angle plus a positive radius, then you just find that radius out on that actual degree measure. What happens if I give you a negative radius is you find that 45 degree, and then you trace back into the negative quadrant from that, so basically a perfect 180 from that. You trace back and head in the radius in that direction. So however you need to write that, I might just say positive radius means on the terminal side of the angle. Negative radius means opposite direction of terminal side. To paraphrase this note, you can just write that polar coordinates, each polar coordinate can be represented in an infinite number of ways. The reason why is because any theta you have, can't you just add 2 pi and come back around to it, right? And come back around. So there's actually infinitely many ways that you could represent this point through different thetas or through negative radiuses. Okay, whereas on the rectangular coordinate system, there is only one XY coordinate for that particular point. There's no other way to represent a rectangular coordinate in more than one way, whereas here I can. All right, so we're going to start nice and simple. All I want you to do for each of these is to plot the point by hand. And then it says to determine the rectangular coordinates of each point. You guys will find this to be pretty simple, so I'm actually just going to do one of the points to show you how that is. That part is pretty easy. Okay, and actually, I'm going to go back up really quickly. Go back up to this drawing. Let's write out our conversion. You guys already know the conversions, but let's just write them out. Okay, for x, on the unit circle, how did you represent the x-coordinate on the unit circle? Cosine. And the radius on the unit circle is 1, right? Do I have a radius of 1 necessarily anymore? So how do you think I'm going to modify that cosine of theta? Very good. So your x-coordinate is r cosine of theta. In other words, if I give you a radius and a theta, you can find the rectangular coordinate for x just by plugging in r and theta and evaluating. How about the y? What will that be? R sine of theta. Very good. So these are the two equations that you will use if you're given polar coordinates and you know r and theta. This is what you will use to get your x and y coordinates to convert. The question is, what if I give you x and y and I want r? All right, the easiest way to find the radius given x and y is going to be to use Pythagorean theorem on this triangle. So in other words, what does r squared equal? Very good, x squared plus y squared. So that will be, if you know x and y, this is going to be how you're going to find the radius. Okay, what do you think is going to be the easiest way to find theta without having to know the radius first? How can you find theta without having to know r? Inverse tangent, yep. So you guys will be doing inverse tangent of what? Y over x. Very good. Yep. So like I said, you guys already know the conversions. We're just using them in a slightly different way now. Okay? All right. So let's go back to that other slide, keeping these in mind. All right, let's first plot these. Then we'll do that rectangular coordinate business. All right, let's say that I want to plot the point P. The way that you do this, so look at P, you've got a radius. Remember, the first number represents your radius. The second represents your angle. Okay, now this particular polar grid that I have happens to just have each quadrant split into 30-degree chunks, right? You guys might throw in a 45-degree angle, or you might cut it into 6 15-degree segments. You know, each polar grid, it just depends on which one you have, might have more or less lines. You should be able to figure out how big each of the chunks are by taking your 90-degree chunk and dividing it by how many lines you have. That will tell you how many degrees you've got, right? How many radiuses do I have on this? 4, right? So this is going to represent a radius of 1, 2, 3, and 4, right? All right, so when I'm plotting 135 degrees, I measure from the horizontal, and I find my 135 degree. Notice I don't have it here, but it's going to be right smack dab between the 120 and the 150, right? And then I'm going to be out on the 4th radius. So my point for P is right there. All right, let's, while we're at point P, find the rectangular coordinates for this guy. How do I find for P the value of x? R over 2. Oh, I see what you're doing. I understand what you're doing. Let's just stick to the regular old, let's just stick to the formula so we can see how to use it in any case, okay? I see what he's doing. He's noticing that since we're at the 45-degree mark, I am equally this far out as I am this far out, right? So that's what he's doing. I want us to find this, though, using the formula, so in case I give you an odd angle, like if I give you 97 degrees, you'll know what to do still, okay? And that's okay, Sam. If for a problem like this on the homework, if you saw that, that's fine. But again, I just want to make sure we all see what to use. Okay, so what would be the formula that we're going to use based on the other slide that we can always use? What is the x-coordinate always going to equal in terms of r and theta? Okay, r, so 4 cosine of theta, right? But what is the cosine of 135? Negative root 2 over 2. Yep. And then you've got 4 times negative root 2 over 2. So the 4 is going to cancel with this denominator 2 to become 2. So this is going to be negative 2 square root of 2. All right. How are you going to find your y coordinate? Yep, so 4 sine of 135 degrees. What is the sine of 135 degrees? Positive root 2 over 2, right? So the only thing that changes here is that we've got a positive value for that. So this will be positive 2 root 2. So your xy coordinate for P is negative 2 root 2 and 2 root 2. All right, that's simple enough. I am not going to do that for Q and R because likewise you would just plug in R and theta and evaluate. Same type of thing, right? Let's at least plot those other points though because those do have some of the other tricks that I wanted you to see. So let's plot point Q. When you're plotting point Q, you should be looking for pi over 6. Where's that? You're 30 degrees, but you've got a negative radius, right? So here's my 30-degree line. Am I on that line? Where do I go? To the 210 that's directly opposite, right? And I'm going to put my radius of 3 down on that side instead. So the negative switched the direction, but I still keep that negative 3. Okay? So this is going to represent my point for Q. Okay, how about R? R, you have negative pi over 2 for your angle, so where's that? Y-axis here? Yeah, down. Okay, so the y-axis down here, and I've got a positive radius, which means I'm going to stay on that actual angle, right? All right, so then I'm going to go 2 on that angle. So my point should be right there. And that is the point for R. Are there any questions on how to plot polar coordinates or how to change from a polar into a rectangular? Both of these should be very easy, and actually you've done the plotting part of this, you've done it in geometry. Don't know if you remember, but you have. Okay, all right, let's move on to some other type of conversion problem. So it says to find all polar coordinates for the rectangular coordinates 6, negative 6 root 3. All right, so for starters, how am I going to find my R? Because I need to find the polar coordinates, which is going to be R theta. How do I find R? Yep, we're going to use the formula R squared equals X squared, and in this case our X is 6 plus Y squared, so negative 6 root 3 squared. All right, now 6 squared is 36, and then negative 6 squared will be 36. Once I square out that root, it'll be times 3, so 36 times 3 is 108. Add those together is 144. So that means that R is equal to what? Huh? Plus or minus 12. Yep, remember you can have a negative radius. Okay, how am I going to find theta without using one of those R values? Huh? Tangent inverse of what? Right, so the y value over the x value. So for us, negative 6 square root of 3 over 6. Notice that your 6's cancel, so you're really looking at tangent inverse of negative square root of 3. So think to yourself on the unit circle. Remember that the tangent is the same as sine over cosine, and the sine is your y value, right? So if you want your sine over cosine to cancel down to root 3, then that means that you want the coordinate with the root 3 to be on top, which means you want the y coordinate to have the root 3, right? All right, so let's go through this one bit at a time. So he said 4 pi over 3. Close. So first of all, just tell me in the first quadrant. Quadrant 1, which value? Is it going to be your pi over 3 or your pi over 6 that's going to have a root 3 on top? Pi over 3. Your 60-degree angle on the unit circle is the one where the coordinates are 1/2 and then square root of 3 over 2, right? So that would give you y value over x value where the root 3 would remain on the top. But I have a negative on this. Which quadrants are your tangent values negative? Quadrants 2 and 4. So in quadrant 2, what is your reference angle to pi over 3 in quadrant 2? To pi over 3. Yep. How about in quadrant 4? 5 pi over 3. What's another way you could write that? Right. So you could have write it as 5 pi over 3, or you could write it as negative pi over 3. Really doesn't matter at that point. Unless they tell you a specific, range that they want you to be in. If they say they want their answers to be from negative pi to pi, then you would be excluding this and including this, right? If they say they want their values to go from 0 to 2 pi, then you would do this and write this as 5 pi over 3. So it just depends. Now here I was told to find all coordinates, so I didn't have to really follow any restriction. I could just write whichever form I liked best, right? Okay, now the difference is that here I'm asking for all polar coordinates, right? So what would I have to do to both of these last solutions? And I'm going to put this down below so that I can add it on. What would make it so that I would get all solutions here? What do I add on? Plus 2 pi k will take me back around to the same of either of these angles, right? All right, so I've got 2 possible thetas, and I've got 2 possible radiuses. I do have to be careful how I pair these. So what I'm going to do is kind of think to myself, all right, where was my rectangular coordinate that I was originally given? Because I have to make sure that I'm picking my r and theta combination so that I'm in that quadrant again, right? So where is the point 6, negative 6 root 3? What quadrant is that in? Quadrant what? Quadrant 4, right. So you're in quadrant 4 for that. You've got an angle, something like that, right? So what you guys have to do is find the combination of r's and thetas that work in quadrant 4. So for an example, if I chose positive radius 12, which angle do I want to choose to make sure I stay in quadrant 4? Yep, you want to choose that negative pi over 3 plus 2 pi k, because the 12 says I'm going to stay exactly on the angle you give me. So I want to give the angle that's in quadrant 4 and then stay on it with a positive radius, right? If I use negative 12, then which angle do I want to use? Yeah, you want to use the 2 pi over 3 plus 2 pi k, because 2 pi over 3 is this angle up here. And when you do that angle with the negative radius combination, it's going to throw you down onto this line, right? So that combination also works. Any questions on that? And again, they might not ask you for all polar coordinates. They may say, find the polar coordinates from 0 to 2 pi, or find the polar coordinates from negative pi to pi, right? So make sure you're watching the wording on that. I did the all solution, so I added 2 pi k. All right. This time, we're working with equations. So notice that in the last 2 examples, I've given you coordinates, and we've just been transferring 1 coordinate from rectangular to polar. I am now giving you a full-on equation which will have a curve, and I'm asking you to transfer that whole curve from polar to rectangular. And then vice versa, we'll do rectangular to polar. All right? So what you guys want to keep in mind as you are going through these types of problems, if you are converting from polar to rectangular, what you need in order to be able to replace something with x, you need to have r cosine of theta exactly in order to replace it with x. Or you need to have r sine of theta to replace it with y. What's one more conversion that we could do that's not a direct x or y but still would get it in terms of x and y? If you had r squared, couldn't you replace r squared with x squared plus y squared? Right? So you are looking to force these types of things. You're looking to force either an r cosine, an r sine, or an r squared. Take a look over here. I've got an r on this side by itself, and I've got a secant on this side by itself. How can I rework this so that I have one of these things? Okay, why do you want to do that?
So then you could cancel out the secant on one side, and then it would be r cosine theta equals -5.
Very good. So just so that people can see that intermediate step, I'm going to rewrite. The secant, remember, is the reciprocal of the cosine, right? So that's why this works. So he's saying, all right, I want to multiply everything by the cosine of theta, right? And in doing that, I'll pick up an r cosine, which is in my little list up here that I want. And then I'll just have a -5 left over on this side. So now that I've got my r cosine of theta, what can I replace it with? X equals -5. Okay? Now you guys can recognize you have now gotten it in rectangular form. You have no y's, but that doesn't matter. The main thing is you have no other variables other than an x and or a y, right? Now it says to identify the shape of the graph. I will also be asking you to, on the test, I'll be asking you to give me the shape and the location of the graph. Okay? Location / size. So you'll want to kind of describe to me what this is. So what is this type of a graph? So what? More specific? Vertical line where? Vertical line at -5. Very good. If this was not a vertical line and it was a slanted line, what I would mean by tell me its location is shape is I would mean tell me where its y-intercept is, tell me what its slope is. That gives me its location and its shape, right? Okay, let's take a look at the next one. Same thing. You are trying to get this stuff out of this. You're close on some things, right? You've got an r. What do you wish that that was? You might wish that that was r squared. You've got a 2 cosine of theta. What might you wish that that was? An r cosine of theta. What do you wish this was? What are you missing on each of those pieces? So what do you think you can do? Multiply by an r. As long as you're doing things that keep the equation balanced, you can do that. All right, so if I multiply by r, I'm going to get my r squared. Now, something you guys were saying was that you wish that this was an r cosine of theta. Would 2r cosine of theta still be okay? Yeah, so that's fine that that 2 is still hanging out. All right, so we've got things that we can replace. R squared can be replaced with, yep, x squared plus y squared. R cosine of theta can be replaced with, I'm going to keep that 2 though, just like I'm going to keep this 3, but then I'm going to replace r sine of theta with a y. Can anyone tell me at this stage in the game what shape this is going to be? I'm hearing some circle out there, right? You're kind of like, that kind of looks like a circle, except for it's got x and y stuff on the other side. We have actually dealt with this at the very, very beginning of the school year, okay? It is a circle, but we're going to have to, because remember on the test, I'm going to be asking you for its location and size. So what are you going to have to tell me about the circle to tell me about its location? What do you need to find? The center. How about its size? The radius. How are you going to get that center and radius out of this? Yep, you complete the square. Very good. So to complete the square, we need to put our x's together and our y's together. So I am going to group x squared minus 2x together. And I am going to group y squared plus 3y together. And this stuff is now equal to 0. But I wanted to complete the square. So what am I adding in with the x's here? How do you complete the square on that? Plus what? 1. Yep, you take half of the middle term and square it. So half the middle term is 1, square it is still 1. If I add 1 onto one side, add 1 to the other. All right, now I need to complete the square on my y stuff. What's that going to be? As a fraction, I don't like decimals on this. 9/4, yeah. Divide 3 by 2, it'll be 3 halves, square it is 9/4. Add 9/4 on one side, add it on the other. Okay, so now that whole point was so that I could write this as one quantity squared for both the x and then the y. So how can I rewrite this grouping right here? X minus 1 squared plus y plus 3 halves squared, and what does that equal? As a fraction, one fraction? 13/4, very good. All right, so what is the shape of this? You already said it's a circle. Where is this circle? Yep, so it's got a center at 1 and what? Negative 3 halves, very good. With a radius of what? Whoa. I heard somebody say it. Yeah, with a radius of square root of 13 over 2. Square rooting that 13/4. You can't square root to 13, so you'll just leave it, and then 4 can be square rooted to 2. Any questions on that problem? On, in general, how to convert between polar to rectangular. You're trying to force this stuff, right? Either by rearranging. So on this one, we just rearranged, right? Or by multiplying something new in to get what you want. All right. As you might have suspected, what's coming next is to convert from a rectangular to a polar. Okay? Now, like I said at the beginning of the period, sometimes graphs are easier as a polar representation. Sometimes they're not. So we're going to look at both, all right? What kind of a shape is this? A line. Is that going to be fairly easy to graph in a rectangular coordinate situation? Absolutely. Let's see what happens when we make it polar. Okay? First of all, how do you make it polar? Huh? Y is what? Yeah. Yeah, exactly. So you just want to replace what is y in r and theta, what is x in r and theta, right? Going from rectangular to polar should always be easy because you will always have an x and you always have a y, and you can always replace the x with r sine of theta. You can always replace the y with r cosine of theta. I think I said that backwards. I did. Switch those up. X with r cosine, y with r sine. Right? So let's take a look at that. In this case, if I have my y value and I replace it, I'm going to have r sine of theta equals 2 times, and then replace, I guess I don't really need a parenthesis, but replace x with r cosine of theta minus 4. Okay, for these equations, what you are going to want to do is solve for r. Just like generally, and not always, like with the circle, we didn't solve for y with the rectangular, but most of the time we'll try and solve for y, right? So in polar, we're always going to try and solve for r. Yeah?
Wait, why do we do that? Because rectangular is like f of x, so here it's f of...
Yeah, so he's asking, the question for that he's asking is, when you look at an xy coordinate, x is our input, right? And I am about to have you put what correlates with the x coordinate as far as, so here, maybe it'll help if I write it up here. Remember we said that we have xy coordinate or we have r theta, right? Notice that I'm telling you in polar or rectangular we usually solve for the y coordinate. And now I'm telling you we're going to solve for the r coordinate. Notice how those two don't match up? Okay? It is because on the polar grid, okay, the radius might occur multiple times. And I know a theta can occur multiple times, but you can be methodical about just when you're... Theta is a better input because you can start at 0, then go to 30, then go to 60, 90, and you can just work your way around the circle and be methodical about it. It's a better input, right? If you put in the radius as your input, you're jumping all over this graph and you have no idea what order to connect them. We're always going to connect these in order of smallest angle to largest angle as we're going through. Does that answer? Yeah.
But why don't they just say the point is theta r?
I don't know. That I can't answer. This is the form they give it. I'm not sure why they did that. All right, so we're going to solve this for r. To do that, I am going to take my 2r cosine of theta, rewriting it on the other side so that I can keep my r on the left. But follow the process here. I'm going to subtract the r sine of theta over. What does that mean it equals? Positive 4, right? Because I took this and I moved it over with this thing, so I'm going to take the 4 and move it over to make it positive, but then I've switched the overall sides. I only did that just to keep r on my left. Now I can take an r out. Okay? And divide. So r is going to equal 4 over 2 cosine of theta plus the sine of theta. In polar form, a linear equation is always going to look like this in polar form. You're always going to have a constant on top, and then you're always going to have some scalars on the cosine and the sine. Yeah?
When you divide it, why did it...
I meant to keep it minus, sorry. Is that what you're about to ask? I just saw it right when you were asking. Yeah. But it will always be a constant on top, and then cosine plus or minus sine with maybe some numbers attached. Okay? This will be a linear looking thing. How is it linear? Let's just plug in some points to see. So remember I said that we like to plug in thetas. What are some easy thetas to plug in? I think 0 is easiest. Right? Okay? What is the cosine at 0? 1. So when theta, and I'm just going to kind of draw a little t-chart so that you guys can follow me here. I'm plugging in 0 for theta, and I'm asking what is your radius? So cosine is 1, sine is 0, right? So that goes away, and you have 4 over 2 is 2. So when I'm on my grid, I am plotting the point 0 degrees, and then a radius of 2 is right there, right? What is another easy point? What is that? I still can't hear what you're saying. 30? Yeah, we could try it. I don't think it's going to be perfect because we've got a root 3 in there then, but we can try it. All right, so if I do 30 degrees, in your head real quick, you've got, what's the cosine at 30 degrees? Root 3 over 2, but then times 2 is going to leave it with just root 3. And then minus the sine is going to be 1/2, right? So it's a kind of ugly, you can punch it into your calculator and see, but you've got 4 divided by the square root of 3 minus 1/2. That's something that I wouldn't want you to do in your head. So you would punch it out on your calculator. Let's see here, what do we get? 4 divided by square root of 3 divided by, or minus 0.5. So I'm getting about 3.2 for that. All right, so let's plot that. If I plot, what did I just say? It was about 3.2? So right about here on that 30-degree mark, maybe? Okay, what do you think, taking a look at where this line is headed, what would be a good point to test? So in other words, if I start to go out to 60 degrees, is that going to land on my grid here? If I'm thinking that this is a line through these 2 points? No, that's not looking very promising, right? Is this line ever going to hit 120 degrees? No. Okay. Take a look. If I'm following this line, I think the next easiest one would be to check on my negative pi over 2, right? I'm not going to write it in because I'm out of space with that created with Dosiri thing, but let's plug in pi over 2 in our head. The cosine is 0, right? And the sine is 1, or I'm sorry, yeah, negative 1. Wait, did we do that right? The sine is negative 1, so this is going to be positive 4. That doesn't look good for us, does it? That should be a negative 4. What happened there?
I think you do have to do it for positive pi over 2, or negative pi over 2.
Oh, isn't that what I did? Wait, what? Oh, no, that's fine. Why is that fine? Because I got a radius of positive 4, right? But remember, the radius, if it's positive, is on the angle you plug in. We plugged in negative pi over 2, right? So if I get a positive radius on that angle, then I'm down on that angle at 4. Sorry, I was having a mental moment there. Does everyone see why that point does land us right where we want it? And how that can get tricky sometimes with that positive radius, how that can be confusing? All right, so now you can see that we do get the line going through all of this stuff, right? So you can see for this particular example, it would have been way easier just to graph this on the regular grid, right? So this is an example where rectangular is our best bet. And even the equation looks better. This equation doesn't look very nice, right? Let's take a look at another one. All right, so you guys can already see what kind of a shape this is. This particular one is not hard to graph on the polar grid at all, or on the rectangular grid, but it's even better in the polar grid, okay? So let's take a look at that, and it's an easy conversion. Do I have to plug in r cosine square, or r cosine of theta and r sine of theta, or do I have a different conversion I can do with this one? What is x squared plus y squared? So this says, whoa, this says r squared equals 25, which means that r equals plus or minus 5. Okay? This equation is a very simple polar equation, and it doesn't have a theta input. So what that means is that for any theta, you have a radius of plus or minus 5, right? Okay, now notice that I only have 4 radiuses on here, so what I'm going to do is say that each one of these radiuses goes by 2's, okay? That way when I'm plotting this thing, I'm noticing that at any theta, I have got a radius at 5, no matter where I am, right? Skip around a little bit here so we can see. Okay, but basically all that's happening then is this shape, draw it as best as I can here, is a circle with a radius of 5. And that is a good polar equation. The polar equation actually represents this a little bit better. It makes more sense in polar than it does rectangular, right? Like you guys know, you're familiar with the form x squared plus y squared equals 25, but that's not obvious to somebody just looking at it that it's a circle. If I gave this to anyone who knows what a radius is, and I said the radius is 5, what shape is it? They would say, hey, it's a circle because you told me a radius is 5, right? That's the only way that makes sense. So in this case, polar is actually the more natural form. Any questions on that? Okay. So now we're going to get into some more complicated shapes. One thing we're going to have to check on these complicated shapes is symmetry. It's going to help us out a little bit, all right? So the graph of a polar equation has the indicated symmetry if either given replacement of r theta is an equivalent polar equation. So what this says is if I replace my theta with a negative theta in my r theta business up here, and I am able to simplify it all down and it ends up being the exact same equation, then it is symmetric about the x-axis. If I replace negatives on both the r and the theta, then it's reflexive about the y. And if I replace the r as negative and it works out, then it's symmetric about the origin. Notice these other versions over here. I'm just going to do one quick example on for the first one to show you what's happening for that, and it's similar for all the rest. Okay. Actually, let's look at the last one just because I have space down there. All right, so let's say that I'm looking at an axis here. Okay. And let's say that I have some line that's drawn with a certain theta, okay? So I'm just going to draw it here for the sake of drawing it. That means that I've got, this is my angle, theta. And let's say that I've specifically given it this radius, right? Sorry, that's really small. If I replace r with negative r, graphically, what does that do? Where does that put me? What quadrant does it put me in if I just replace the r with a negative r? Right. All it does is it takes me down here, right? See what I'm saying? And that is symmetric about the origin then. Okay? Notice that if I kept the r positive and I just added pi to theta, doesn't that take me to the same exact spot? So these two things are actually equivalent, right? Similar if you look up here. So let me do that one really quickly with a branch. Let's take a look up at the first one. If I replace the theta with a negative theta, that takes me down here, doesn't it? Because it's going to map out that theta this direction instead. So you can see how that gives you symmetry about the x-axis. And again, this works because if I take pi minus theta, right, pi minus theta is going to take me right here. If I take pi and I subtract off that value, it's going to take me on this line. And then if I give it a negative radius, it throws me down onto the same exact line. So again, these two things are equivalent. I'm not going to do the second one because it's a similar reasoning. You guys can think through that, and it would be good for you to think through it on your own. Questions on how we're checking symmetry here? No? Okay. I'm just going to give you a little tip for how I remember. I just like working with these. Okay, I don't really do this over here. I always remember the y-axis is both. I just memorized that. You change both the r and the theta. The way I determine between x-axis and origin, whether it's the r or the theta, is sort of strange, but O has origin, right? So O should stay the same. The O-looking thing should stay the same. It's not really mathematical at all. It's just a gimmick to remember. So then the x-axis is the one that doesn't have an O, so the O should change, right? Okay, that's just a way you can remember that. Okay, now we're going to look at the different types of graphs that we are going to have. You will have to visually tell me sometimes what the symmetry is. So looking at this visually, what is your symmetry? X-axis. What is this? What is this? What? Origin. What is this? I wouldn't say that that's symmetric about the origin. I would say it's symmetric about the x and the y, though. Yeah? Remember, the origin is if you reflected over this line, it should be equal. Visualize reflecting that. That's not going to map over to each other very well. Okay, so now let's talk about what the shapes' names are. You've got circles. I don't know if I say this right. If somebody knows, let me know. I just call it lemniscates, but I'm pretty sure that that's wrong. So I haven't learned how to say that. Doesn't really, yeah, I don't really care. So the main thing to me, I do it very phonetically, but guys, for these, what I am going to do when you are taking the test is I'm not going to write circle on the board, but I will write this word and the next one on the board, okay? And you will have to be able to identify whether it's that shape. But like as far as having the spelling in front of you, you know, I'll give you that. All right. Things to watch out for. So for a circle, the circle's equation is always going to equal a radius, not squared, equal to some sort of a scalar times the cosine or the sine of a regular old angle theta. Where that circle is going to depend on positives and negatives and cosines and sines and thing. So don't just memorize like, oh, that was a circle on top. It might be a circle on bottom. It might be a circle on the left rather than the right. Okay? So you'll have to do some points to figure that out, but you can at least know that you're expecting a circle if you have r equals like 3 sine of theta. Something like that. Okay? What is, you guys, analyze this really quickly for me. How far out is this point going to go? Without even having to know, how far out do you think that point's going to go? What is the cosine of 0? 1. So how far out is that going to go? No. A. Because cosine of 0 is going to be 1, but you're going to have that a multiplied in front, right? So you know that a circle is always going to go from 0 to its a value is how big that r value is. Okay, that's your maximum r value. Since it's a circle, then you know it's split evenly this way, right? So you would just, your range would be half of a to half of a on this one, right? Now technically, you guys, your domain, that just tells you that this is bounded. Your domain is not actually from 0 to 4. That is just your maximum r value. Because on what is your input in this function? What is your input? Theta, right? Is there any time, like, are you going from 0 to 4 for theta? Not so much, right? So that's kind of confusing to some people, right? They're kind of like, whoa, what's happening there? Okay? Your input here is actually negative infinity to infinity because I can plug in any old theta. The thing that's going to happen is it's just going to keep on cycling around the circle, so your range is what is bounded, okay? All right. This lemniscates. What? I have no idea what it's. Lemon skates? Lemon skates? Lemon scones. The lemon scones. All right. Well, that might help you remember. This is a good little learning gimmick because if we call them lemon scones, then you have 2 scones. Okay? All right. This particular shape, notice it has an infinity-looking thing. It might go diagonal. It might be diagonal the other way. It might be up and down. It might be horizontal. These are just a couple of different ways they can look. The main thing to watch out for is what is the equation, right? So notice that for these, you've got an r squared this time, and your a is squared. And also, what else is different? You've got a 2 theta, specifically. All right? You have to have the 2 theta for it to be a lemon scone. Okay? Yeah?
So you're saying they can, be in any...
Yeah, so you'll have to, I'll show you guys that, but you're going to have to plot some points and you're going to have to kind of analyze it.
So how do you know which one it is?
Like I said, you will have to plot some points and just see where it goes. That's all there is to it. You're not going to pick one right off the bat. You're just going to start plotting points and once you've got one leaf, the other one is going to be in the exact opposite direction. But you will have to just plot points to find that first leaf. Okay, do we all have this down? Again, the main thing, you guys, is can you look at the equation and tell me what shape it is? Right? How big do you think this radius gets? This looks like the maximum radius right here, right? At 45 degrees. See that? But if you have 45 degrees, what's your actual input? 90, right? What's the sign of 90 here? 1. So what is r going to be? This all went away, right? At 45 degrees, that all disappeared. So if r squared is a squared, what is r? At 45, right? So that still is your biggest outward value. Now, if you looked at this one, it would be similar, except for notice that your biggest value happens when theta is 0, right? Plug in 0, it still is going to be 0. Cosine of 0 is 1. Still r squared equals a squared, right? Any questions on that? Okay. Limicons. All right. I personally picture, when I think of this shape, I am picturing a man on a toilet.
How do you get that from the first one?
Well, he's pooping or something, but. All right. Yeah, so I kind of, the curly Q one, he's pooping. This one, he's got a big butt crease. This one, not so much of a butt crease. And this one's just the empty toilet seat, okay? So, I don't know how you want to connect the word limacon to that. Lima beans make you poop, I don't know. But that might help you remember what shape you're expecting for a limacon, though, right? Because it could be easy for you guys to mix up a lemniscate, whatever it is, and a limacon. So those are some things that you can do to help you remember. Lemon scones, there's 2 of them, infinity shaped. Limacon, lima beans make you poop, so you're looking at the toilet shape. Okay, look at the equation for this one. This one, it looks really similar to a circle, but what have I changed? Remember, this part was very similar to what we had for the circle. I have now added or subtracted a constant onto the circle equation, right? Depending on your combination of A or B is going to tell you whether you have the pooper, the butt crease, less of a butt crease, or a toilet, okay? A over B, if A over B, so you're looking at the constant that's by itself over the constant that's attached to the sign, right? If that is less than 1, you've got the pooper. If you guys can't handle it, I can talk about this mathematically, but I truly think it will help make more sense if I describe it this way. If A over B is 1, so in other words, if A and B are the same exact value, then you're going to have butt crease. Okay? I'm trying to think of ways that you could all correlate this. So if it's less than 1, then he has emptied his body. Because he has removed it. It's less, right? Okay? If it's equal, then he's got a nice shapely butt because he's doing things just right. If it's in between 1 and 2, maybe eating a little too much, but we still have a butt. But it's starting to get flat, you know how that happens? If it's greater than 2, then we've definitely eaten way too much and we have no more shape whatsoever other than a big round ball. Okay. But will you remember? Yes. Okay, that's the point. All right, graph analysis. You can plug in any theta, right? Agreed? Yeah. Okay. The range is a little bit awkward because it's not perfectly centered anymore. So the range goes from A minus B to A plus B. Guys, the range in this case, because some of you are probably like, well, what does that mean? The range in this case is all overall R values, all around, okay? That's not just talking about the vertical change. It's talking about everything. Because range is your output R, right? These are both continuous and bounded. In other words, I wouldn't have to lift up my pencil to sketch this. I would just keep on going, right? And I would never have to lift up my pencil, okay? Bounded meaning I can find an upper value and a lower value all around it. It doesn't go to infinity in any of the directions, right? For the symmetry, you will just need to do your symmetry test to see what to expect. Visually, once you have a graph visually, what is this symmetric to? Y-axis, X, X, Y, right? So visually, it's pretty easy to tell. Sometimes you're going to have to do that analysis before you graph it so that you can kind of use it to your advantage in your graph. Okay? Your maximum R value here is going to be A plus B. And of course, there's no asymptotes. All right. Last type of graph that I'm going to describe are rose curves. They look like a rose, so it makes sense, right? Notice that these look very similar to two things. It looks really similar to the circle formula, but it also looks kind of similar to that lemniscates one, right? Lemonscones one, right? What's the differences? Here, it's not a circle because we're assuming that it has a value. It has a multiple angle is what we're assuming. Okay? It's also not a lemniscates or a lemonscone because why? What does a lemonscone's equation have that this does not? R squared, right? All right, some things to watch for. Domain is all reals. These are all going to have some really nice symmetry going on, okay? But the range is going to go from negative A to A. So the petals basically could go out in a negative radius direction of A or a positive radius direction of A. Continuous and bounded should be obvious. Symmetry test, if I ask you to do it algebraically, you'll do it. If you're looking visually, what is this? Huh? But what's its symmetry? Is it symmetric about the x? Yes. The y? Origin? Yes. Same with this one, right? This is symmetric about x, y, and origin. How about this one? Origin only? Right? If you reflect it over, actually, not even, right? It doesn't look, oh yeah, it is over the x. Thank you. How did I not see that? Yeah, it is reflexive over the x. Thank you for seeing that. Not the origin, though. Otherwise, this leaf right here would have reflected perfectly onto the y-axis, and it didn't. How about this one? Y, right? Maximum radius value is your A, just like on the circle. No asymptotes. And then the next note to make is that the number of petals to expect depends on whether you have an even multiple of theta or not. If you have an even multiple of theta, you will have double that number of petals. If you have an odd multiple of theta, you will have exactly that number of petals. If you want to copy this down and you didn't get it, please look in the textbook for section 6.5. We'll have all this. Let's take a look at how we do this. So it says analyze and sketch the polar graph. There are certain ones of these, you guys, that I think would be easy enough for you to do by hand, and there are certain ones that, you know, I don't really want you to have to do by hand and that I would have you do on the calculator instead. What you should be able to do is a graph analysis first to kind of guess what you're going to get and then see what you get. So for the graph analysis, can you tell me what type of a shape this graph has? So look at the equation form and tell me what type of form it is. You've got, it's not perfect to anything, but what does it look closest to? Not a lemon scone. Not a rose curve. I would say it's got an A plus a B value, right? The only equation I gave you where you had something added or subtracted on was a limacon. Okay? So in your head, you're thinking limacon, what kind of a shape of a graph is this going to be? In general. Like, what of those that I talked about is it? Is it the circle? Is it the one that's like an infinity shape? Is it the toilet seat shape? Is it the rose? What is it? Huh? The toilet seats, right? It's the butts. Okay, the question is, what type of, are you expecting a curlicue in this? Are you expecting just a butt crease? Are you expecting a flattened butt crease? Are you expecting no crease whatsoever? A over B is 1 over 2, which is less than 1, which means that it has the poop, right? Because he's lessing it all. He's lessing himself. Okay, so that's what we are expecting in shape. Okay, I am expecting this sort of a shape. Now the question is, I've got this 3 theta business. What do you think that 3 theta business is going to do? And actually, let me kind of do that a little better. What do you think that is going to do? Think about what it did in the rose petals. In the rose petals, it made more of the petals, right? So what do you think is going to happen with this? You might have 3 of them, right? Yeah? What is the domain? Yep. What is the range? So I should have this. -1 to 3 maybe? Okay. Domain range, what else did I have you guys do? Let's try a symmetry. First, by hand. What do we try replacing? Remember, you do a combination of, and I'm just going to kind of do this in my head. Well, maybe not. So if I replace with a negative radius, does my equation completely change? Or can I modify it so that it's exactly the same as it was originally? I'd say no. There's nothing I can do there to get that to be back to the original. What if I replace a negative theta? Is cosine an even or an odd function? Even, right? So when you have a negative inside, does it alter your function for an even function? So is that the same? Which means that this is at least symmetric about the what? If I can replace a negative theta, what is it symmetric about at least? Remember, oh wait, I lied. X-axis, yeah, thank you. So it's at least symmetric about the x-axis. I have already found that if I replace it with a negative r, that's going to change it. So if I replace it with a negative r and a negative theta, the theta will go positive, but the negative r will change it again, right? So the best I have is symmetry about the x-axis. What's your maximum r value here? Three. Yep. It's the maximum of your range because you're looking at the maximum that your rose petal goes out to, right? All right. For a problem like this, I am not going to have you do that by hand, and I'm just going to explain why real quick. When you put this 3 theta in, what's going to happen is you want your inputs to be on our normal plugins for the unit circle if you were doing this by hand. You'd want to have, you'd be wanting to evaluate 0 degrees, 30 degrees, 45 degrees, 60 degrees, 90 degrees, right? And then around. What happens when you make this a 3 theta? So let's say I wanted to evaluate 30 degrees. What would theta have to be in order to evaluate 30 degrees? 10, right? And then if I wanted to evaluate at 45 degrees, it would have to be 15, right? So what happens when I put in this multiple of an angle is I have to go by smaller increments of theta, which means to get all the way around the circle is going to take a heck of a lot longer. Because I'm going to have to go by 10 degrees, 15 degrees, 20 degrees, 30 degrees, right? It's going to be smaller increments. That's going to be a pain in the butt to do by hand. So let's do this one on the calculator. And this is where I'm going to lose all that work I just wrote on there, so make sure that you had all that jotted down. All right, so let me pull up that calculator. Where is it? There it is. All right, so how do you plot things on your calculator in polar? Go to the same place we went to the other day for parametric. So go to mode. And this time you're going to scroll down and change it to POL for polar. Press enter, and then go to y equals. From here it should be pretty self-explanatory. You are typing in your R equation. So we will type in 1 minus 2 cosine of 3. And then if you press that X key, it's going to do theta since it knows it's in parametric. Then we want to go to our window. We want our thetas to go all the way around the circle, so from 0 to 2 pi, and you can see mine's in 2 pi because it's 6.28, blah, blah, blah. If yours is not, change it to 2 pi. Theta step, you can kind of make that be whatever you want. I'm going to leave it as what it is. It should be fine. It should be small, though, at least. You might want to go by at least 1 degree. X min and max. So I already saw that my biggest radius was going to be 3. So I want my X min and max to contain that. I'm going to write mine as -4 to 4 to contain it all. For both the X and the Y, because the X and the Y can both be the radius. Then I will graph it. Whee! All right. So what you see here, you guys, is you did get that little pooper thing 3 times, right? You got symmetry about the x-axis like we said we would. The radius of -1 are the little inner loops. Those little radiuses are going out to 1 in a negative direction from the angle that it's at. So that's what that's all about. My biggest radius is 3 on the x-axis out here, right? That's my biggest radius out there. Does everyone see how this graph correlates with all of our analysis that we had written here before? Yes, no? Yes? Okay, if I asked you to graph this on the calculator on the test and then put it on here, find some key points. So like, kind of try and figure out where that value occurs so that you can plot it on your map. But try and do the best you can to transfer this onto a polar graph is basically what I'll be looking for. Key points, connect them in the loops is fine. Like this looks like to me that it's going out to 60 degrees or something around there, right? Any questions on how to do this on the calculator? I'm close on time, so I'm going to kind of move on pretty quickly here. Okay. Next example. This is one that we would want to do by hand. I'm going to actually skip this one and come back to it on Monday. Or actually, can you guys stay after for like 5 minutes? Is there anyone who can't stay for 5 minutes? Okay, so for this one, you guys, we want to do this by hand. I'm going to leave the analysis to you guys so that we can save some time. Oh, that's not the one I wanted to be on. I wanted to be on this one. All right. I'm going to save the analysis for you guys, but basically, what shape are you expecting with the r squared? Right? You've got r squared, so you're expecting a lemon skate. So you're expecting a infinity sign somewhere, right? So if you can get one of those infinity loops, that will be good, right? All you have to do to graph these, so you'll go through and do your analysis just like we did the last one with the domain, the range, and all that jazz. I trust that you can kind of keep up with that. In order to graph this, what you want to do is make a t-chart of theta r values and start plotting them. So theta is our input, r is our output. You will need a calculator for this because we're going to have to square root some numbers. Okay? So theta, the first theta to plug in will always be 0. That's your easiest one. If I plug in 0, what's the sign of 0? 0. Done. Okay? So I'm going to plot, I'm going to plot that point at 0, 0. Okay? Then I've got a point at, what's the next degree I would want to plug in? So I want 30 degrees, which means I should plug in 15 for theta in order to evaluate a 30-degree mark, right? So what is the sine of 30 degrees? Sine. 1/2. Very good. I'm going to take half of that, but then square root it to get r, right? So I'm going to take the square root of 4.5. That is approximately 2.1. Go over and plot that. So that's at 15. That's going to be halfway to the 30. At 2.1, that's about right there. If you have to go, the online homework is posted. I will post this as well tonight. Otherwise, I'm going to stay and do this. Okay? And for those of you who want to stay, you can. If you're going, please go quietly so that it's not messing with my recording. Please just get your stuff and get out as quietly as you can. So try not to throw your stuff around. All right. The next degree I might plug in. I don't really care about the 45 because I don't have anything that's nice to plug in to multiply by 2 to get evenly to 45. So I'm going to jump straight to 60. What's the next angle I'm looking at then? 30, right? What is the sine of 60 degrees? Because once I plug in 30, I'm going to get 60. Hold on, let's pause it. Okay. So if I plug in 30 for theta, I'm evaluating 60 then. Sine of 60 is, so I'll do 9 times root 3 over 2 on my calculator, square root it, right? So if I do that, 9 times the square root of 3, make sure you close your parenthesis, divide it by 2, and then take that square root, I'm getting about 2.8. So I will go over to my graph and I will plot that. So 2.8 at 30. is going to be about right here. Okay, the next angle that would be easy for me to get to would be 90, right? What would I plug in order to evaluate 90? 45, right? What is the sine of 90 degrees? 1 times 9 is 9, square root it is 3. One thing I want you guys to now do is use your knowledge. The next angle, you can see that I'm going by 15-degree increments here, right? So the next thing that I'm going to do is going to be 60. That's going to be 120. But does the sine value change over the or over the y-axis from quadrant 1 to quadrant 2? Do we remain with positive y values? So this 60-degree angle is going to be the same as that 30-degree angle over the axis, right? And that 15-degree angle is going to be the same as my 75. And by the time I get to 90, it's going to be the same as the original, right? So if I plot all those points, I get right here for the 60, 75, I'm about right here. Whoa. Hold on. Go away. Okay. I'm about right here. I've got one loop of my lemon scones, and since you have the one loop, you know your other loop is a perfect reflection of that, right? So I know I'm going to have a point. This point is going to reflect perfectly here, so on and so forth. So I'm just going to kind of jot those out nice and easily. So you can see that knowing the shape of a graph is really going to help you when you're graphing it, right? Whoa, I did that in the wrong place, didn't I? Can everyone see what I did there? I was too far up on that. So I should really be, hold on, right there, and then right there, right there, right there. There we go. That's better. There's your leaf, right? Okay, and then you would do the analysis the same. This last one is only going to take me about 1 minute, so please hang in there. Thank you for staying. Okay, this last example, do you have to evaluate any sines or cosines? No, right? You're using, the one thing to watch, you guys, is that you are using theta in radians, okay? So when I draw my t-chart here, I've got theta inputs, r outputs. If I plug in theta as 0, so is your radius. If I plug in theta as pi over 6, then you would go to your calculator and see what is pi over 6. It is about 1/2. Then I would go to pi over 3. Oh, and I've got negative r, so that's going to be negative. Then I've got pi over 3. Type that into your calculator. That's going to be about a negative 1.0. Pi over 2. Plug that in. That's going to be about a negative 1.6. It's going to keep on going. Does my theta ever stop growing? Once I go a full revolution around, does it start back at 0 or does it keep on getting bigger? So you'll notice that what's going to happen here is as I go around and plot these points, so I had a point at 0, 0. When I was at pi over 6, I had a negative radius of 1/2, so I'm going to be down here. And then I had at pi over 3 a negative radius of negative 1, that's down. At pi over 2, negative 1.6. You can see that what's going to happen is this radius is going to keep on growing as theta keeps on growing, and theta is going to keep on spiraling around. So what happens? This spirals. I'm not going to get it perfectly right now, but you can see that that's what happens, right? This is called an Archimedes spiral. It's a unique one, but it's very easy to do. Thank you for staying. Homework is online. I'll see you guys next week.